Hello, my little turtle doves. This is we're going on with a Barker past paper, the Extension 1, Semester 1, still doing question 11, up to 11E, and it is a circle geometry question that relies on a few circle geometry properties, but it comes down to similar triangle proofs. So with like these questions where we've got triangles and we have to prove that they're similar or congruent, the person with the best diagram wins the day. So very important to get your diagrams up and running. So I'll just read the question. So we've got this circle here, and PT is a tangent to this circle. And that, because we've got a tangent to a circle, we should be thinking alternate segment theorem. And I'll talk about that in a minute. But so we've got this PT, which is a tangent to this circle, and QR is a secant, just meaning that it's a chord, but then it kind of keeps going through it. And the line QR, which is this, intersects PT at this point T. So that's just describing the diagram. Our first job, which we've got to do, is prove this, and it's a 2-marker, prove that the triangles PRT, so that's this little one here, PRT, and QPT, this bigger one, QPT. We've got to prove that they're similar. Okay, so the first thing that I would strongly recommend is drawing up both triangles individually in a way that, well, we know they're going to be similar because we're being proved to do it, in a way that so that their corresponding sides match up. So, and I'll talk more about that in a minute. So the theorem that we're going to use to prove things are similar, which is probably the most common one used in these questions in similar triangles, sorry, is this angle theorem, whereby if two triangles all have the same angles, internal angles, then they're similar. So what we're going to do is, you can see just the easiest one, PTR, which is this little sucker, or alternatively this little dot over here that I've drawn. So I've just drawn these two triangles, the one that we're trying to prove. So this is PTR. And what I've done here with this blue triangle is, so this is QTP, but you'll see it's not the same as this QTP. It's upside down. And the reason I've done that is, it's like I've got this Q here, picked it up, and then put it over there and left this PT the same, like down here. So I've just picked that up and put it there, and the triangle's moved with it. And that's what we've got down here. And the reason why that is because the sides are gonna match up this way, and I'll tell you why in a minute, why hopefully make it a bit more clear why I might have done that. So you can see that this PTR, which is this angle, is exactly the same as QTP, which is this one, QTP, because they're just the same angle. So I've written here angle QTP, which is this one, equals angle RTP, which is this one, because they're common, which just means common to both sides. Now, let me talk about this. This next step is called the alternate segment theorem, and I've got to talk about now what that actually means. So this is the general theorem. So say you've got a circle here, okay? And there's a tangent, which means it just touches the point on the circle and keeps on going. Then the angle between the tangent and the chord, so that's this red one, say, is equal to the angle in the alternate segment, which would be this one over here, A. And let me talk about what this means, the angle in the alternate segment. So say this is the chord what we're talking about here, this one just here. Then it separates it up into the major segment, the one with more space, and the minor segment. And this chord, this angle here between this chord here and this tangent here are at the moment in this minor segment. And the alternate segment is the major one over here. So the angle between the tangent and the chord, this one here, is equal to the angle in the alternate. So this is the minor segment, and we're going to the other one, the alternate one, the major segment. So that's this one over here. Or it works the other way as well. So this is the angle now. So say now we're using this as the chord. And we can say, okay, the angle between the tangent and the chord. So this is a tangent and this is the chord. So now this would be the minor segment, and this would be the major segment, because this side here has got less stuff in it, and this side's got more stuff in it, more space. So the angle between this tangent and this chord is equal to the angle in the alternate segment, which is this thing over here, this little blue B. So how that relates to this diagram is that we've got, what's a nice color? So this blue, so here we've got a tangent. The angle between, and this is a chord, so PT is a tangent and PR is a chord. So the angle between the tangent and the chord, which is of course this, is equal to the angle in the alternate segment. So this is here is the minor and this is the major. So this is the angle in the alternate segment. Beautiful. So this angle here, so we'll call it alpha, is the same as that angle there, which we'll call alpha, according to the alternate segment theorem. So beautiful. So let me put that on our diagram now. So the angle RPT, which is this one here, RPT is alpha. And this angle here, RQP, no, we'll say TQP. So this one here is alpha. And you can see now, because of the way that I've drawn this diagram earlier, that these angles align with each other. And so these angles are the same. And because we've got two angles the same in a triangle, this here is going to be, we could be really technical and make that 180 minus alpha minus just the dot, because that's what this angle is, because it's 180 degrees in a triangle. And that would mean the same thing, the same logic here. And you can see that these three triangles, these two triangles all have the same three angles in corresponding positions. So you'd say, therefore, triangle, just write what they did. So PRT, so this one here, PRT is similar. So this is the sign for similar. The way I remember that is this is congruent because it's like really equal to, and the other one's just similar. And QPT, so that's this one, triangle QPT, and then your reason is angle, angle, angle. Beautiful. So just to reinforce that, the main thing with these questions is you get your triangles and draw them up and in such a way that the angles will correspond. So the first thing I did is I thought, oh, tangent going through a circle, it's probably going to be the alternate angle theorem or alternate segment theorem, because when you've got a tangent going through a circle, it's just like alarm bells should be going like ring, ring, ring. It's probably going to be this theorem down here. So then I thought, okay, well, that means if we're using the alternate angle theorem, then this angle here is equal to that angle there. That's probably going to be, which probably suggests to me that it's going to be an angle, angle, angle kind of problem. So how can I rearrange and flip these triangles about such that this angle and this angle will be in the same part? And the answer to that is, of course, just getting this Q here and flipping it over there. So we've got this PTQ that kind of looks similar to the triangle above. So hopefully that was clear. That was just part one, and it's just the main part. Now what we've got to do is hence prove, which means using what we've just worked out, which is this, prove that this formula, PT squared equals QT times RT. So what we're going to do is, you can tell that PT is in both triangles, this PT. So hopefully that's where we're going to get this PT squared from. And we're going to use the notion that similar triangles have sides in the corresponding sides in the same ratio. So if we say PT, which is this side, over RT, that has to be in the same ratio, just because these triangles are similar, as QT over PT. So that means because these triangles are in the same proportions, because they're similar, this side over this one has to be the same as this side over this one. So what that means is now we can just cross multiply, and we're going to get PT squared. So this times that is PT squared, which equals RT. This times that times QT. Beautiful. So there we go. That's what we had to prove. You can tell that's what we needed there. So that's 3 marks in the bag. You're welcome. Thanks for coming. I've just got under my 10 minutes, which is beautiful. I'll see you guys in the next one.